Hello everyone, my name is James Glassbrenner, and I'm currently a postdoc at the Naval Research Laboratory. The following is a pre-recorded version of the invited talk that I gave at the 2015 APS March meeting. This talk was held in session S31, which was titled Focus Session, Spin-Dependent Phenomena in Semiconductors, Magnetic Semiconductors, which was held in room 207A. My actual talk took place on March 5th, 2015 at 8:36 a.m. The title of my talk is Theory of the Novel Manganese-Doped 225 Dilute Magnetic Semiconductors. So, how do dilute magnetic semiconductors slot in with today's electronics technology? First, to quickly review, we can roughly split electronics components into two broad classes: components that are made out of metals and components that are made out of semiconductors. Now, we utilize magnetic metals for information storage, such as what we use in our hard drives. On the other hand, we utilize non-magnetic semiconductors for the processing of information through things such as transistors. These, of course, make up the central processing units, which are the brain of our computers. Now, to date, we have typically kept these two classes of materials separate within our consumer products. But there is hope to combine them to form new and novel devices, such as magnetic random access memory and also spin transistors. It should be noted that there's been a little more success in creating MRAM over viable spin transistors. However, integrating magnets and semiconductors hasn't been straightforward. A fundamental obstacle has been the impedance mismatch between these material classes, which will destroy your spin polarization. Now, one common solution is to place a resistive barrier at the magnet and semiconductor interface, but this does have the overall drawback of limiting your current. Now, another solution is to get around this impedance mismatch entirely by using magnetic semiconductors, and it turns out that these may be the key ingredient to achieving this synthesis. The dilute magnetic semiconductor field, or DMS field, has been active for over 10 years with a variety of different materials being studied. Contained within this graphic is an attempt to broadly summarize the state of the field. Note that within this discussion, we are going to stick with prototypical examples, and I'm also going to paint with broad strokes with the aim to motivate why we may want to look at alternative classes of materials. There are two broad classes which have received attention, the 2,6 and 3,5 groups of DMS. One of the central areas of study within this field has been how to synthesize and engineer these materials, which contain significant complexity. In the 2,6 materials, manganese is isovalent with the group 2 ions, so there is a lack of charge carriers, and also robust ferromagnetism would be elusive. In the 3,5 materials, manganese both simultaneously spin and charge dopes the system, which complicates theoretical understanding. There is also a tendency towards the formation of magnetic clusters and also interstitial impurities, which also presents challenges for both theory and synthesis. Similar challenges also exist in the 4 group of DMS as well. An alternative way forward, then, is to seek a new class of DMS that avoids some of these problems right from the start. And it turns out that a crystal structure that is familiar to researchers in the iron-based superconductivity field may just provide that new route. In the iron-based superconductivity field, there are the 122 class of materials which possess a robust and versatile crystal structure, which you see depicted over here on the left. The prototypical example is barium iron arsenic, which has a planar structure with iron planes that form a square two-dimensional lattice. We note that this structure stands up remarkably well to the substitution in and out of different ions. For example, if you replace all of the iron atoms with manganese, the same structure remains stable, and you get a new material, barium manganese arsenic. This material is an antiferromagnetic Mott-Stoner insulator. In addition, you can hole dope the material by replacing some of your barium atoms with potassium, and this will induce a weak ferromagnetism. That weak ferromagnetism was studied in the following experimental paper, and in the following theoretical paper in PRB Rapid Communications, we explained that this weak ferromagnetism is due to an on-site canting of the manganese moments. Even more interesting is if you replace iron with zinc. You end up with barium zinc arsenic, a band insulator in density functional theory, and a semiconductor in experiment. You can then create a dilute magnetic semiconductor by doping it with manganese, and then you can induce a net ferromagnetism by hole doping it with potassium. Unlike the standard DMS materials, here we have an independent control of hole doping and magnetic doping, which is useful for material synthesis, and also this independence means that there is a shot at developing a theory of the magnetic interactions in these systems. In both barium manganese arsenic and manganese doped barium zinc arsenic, we saw that we had the onset of ferromagnetic order upon hole doping. In barium manganese arsenic, it is clear that this is due to a competition between superexchange and double exchange, and that this is what leads to the weak ferromagnetic canting. Now, in the case of barium zinc arsenic, it is less obvious what is going on, but in the end, we're going to conclude that the same mechanisms are again at play. The rest of this talk, then, is going to be dedicated to exploring the magnetic interactions in these systems and convincing you of these two basic points. Before moving on, I want to again emphasize the versatility of the crystal structures common to the iron-based superconductivity field. Beyond the 122 structure pictured here, there are several other classes, such as the 111 and 1111 classes, all of which have this planar iron arsenic structure. These structures in general hold up very well to the swapping out of one atom for another. So zinc has successfully replaced iron in both the 111 and 1111 cases with the prototypical examples that I have pictured here. In all cases, they are band insulators. So within this entire class of iron-based superconductors, we have a rich collection of new potential DMS materials to explore. And even better, we can bring our knowledge from the iron-based superconductivity field and apply it to these materials. Let's review the experimental situation for manganese and potassium-doped barium zinc arsenic, which was first studied and reviewed by Zhao et al. In the following Nature Communications paper. This material has a Curie temperature of 230 Kelvin under optimal doping, which is already higher than the maximum of 190 Kelvin attained in manganese-doped gallium arsenide. The coercive field is also 10 to the 4th Oersted at 2 Kelvin, which we should note is 2 orders of magnitude higher than manganese-doped gallium arsenide. Finally, high-temperature susceptibility measurements indicate effective moments of 5 Bohr magnetons per manganese, which indicates that the manganese ion is in the 2+ charged state. There is a mystery, though. Direct magnetization measurements indicate a sharp reduction in the local moment. Here we see that for all doping levels, the magnetization per manganese does not exceed 2 Bohr magnetons. Now, the authors speculated that this could be due to the formation of antiferromagnetic singlets that compete against a longer-range ferromagnetic ordering, although no exact mechanism was specified. The magnetization per manganese also exhibits a curious doping dependence, which eluded explanation in the original paper. Here we note that with increasing hole doping, the magnetization generally increases. A successful theory should be able to account for this dependence and overall reduction. To answer these and other questions, we turn to first principles methods. For the rest of my talk, I will discuss results obtained using 2 different methods, a pseudopotential method implemented in the code VASP, and also a full potential linear augmented plane wave method implemented in the code ELK. For all total energy calculations, we use the generalized gradient approximation, or GGA approximation, to the exchange correlation potential. For investigating specific details of the band structure, we also used the so-called modified Becker-Johnson functional, a meta-GGA method that is used to replicate the band gap of a variety of semiconductors, with barium zinc arsenic being no exception. For magnetic doping, we directly substitute manganese for zinc in our supercells, while for hole doping, we use the virtual crystal approximation, in which we substitute our barium atoms with a fictitious atom of fractional charge to impart holes into the system. Finally, when we start discussing the magnetic exchange, we obtained our parameters by fitting our total energy calculations to the classical Heisenberg model. The way this was done is we took two manganese atoms and then placed them at various neighbor distances, such as you see in the image on the right. We then calculated the total energy for a ferromagnetic alignment and also an antiferromagnetic alignment. We did this for the different neighbor pairs, and then we collected all those energies together and fitted them to our model, allowing us to extract the coefficients. So, to begin, we need to answer two basic questions about our system. 1. Can manganese impurities ever be interstitial? If they are, this can have implications on the nature of the magnetic interaction in this system. 2. What is the manganese charge state? The magnetization measurements we saw in the previous slide call into question whether or not it's in 2+, and our theoretical analysis could be complicated if the answer is something other than 2+. To begin, we consider the case of manganese impurities. The following are relaxed structures obtained via DFT for a substitutional manganese impurity and also an interstitial manganese impurity. To figure out which configuration is more energetically stable, we cannot simply compare the total energy calculation for each supercell. Note that the number of atoms in each cell is different. Instead, we need to compare free energies. We can write down an expression for the free energy for each cell, and we obtain the following. We find that the free energy difference, using our calculations, is equal to negative 1.09 electron volts plus the chemical potential of zinc. The chemical potential of zinc can also be constrained with our calculations, and we find that it is in the following range. As you can clearly see, if you plug the range of the chemical potential of zinc into our free energy difference, we see that the substitutional impurity is highly energetically preferred over the interstitial one. That means, for all intents and purposes, interstitial impurities simply do not appear within this system, and for the rest of our talk, we're not going to consider them in any subsequent analysis. This is the band structure, resolved by atomic character for pure barium-zinc arsenic. The first thing we note here is that the band gap is small and indirect, equal to about 0.25 electron volts. The top of the valence bands, as you can see here, are primarily of arsenic character, while the bottom of the conduction bands are primarily of barium character. And then mixed in throughout these bands is some of our zinc character. Now, we want to see what happens when we add a manganese atom into this system, and in order to evaluate that, it's easier to look at the density of states. Here I plot the total spin-resolved density of states, as well as the manganese-resolved partial density of states. The sharp peaks that we see here and here are primarily of 3D electronic character, and we see that the majority states are fully occupied and the minority states are fully unoccupied. Therefore, we can conclude that the manganese atom is in the 2+ charge state and is therefore isovalent with the zinc atoms. This is important because it means when we swap out our zinc atoms for manganese, we are not introducing any spurious charge carriers into the system. Next, I want to discuss the hybridization of the manganese moments with the occupied arsenic states and the unoccupied barium states. For this, it is easier to refer to the following schematic. Upon hybridization, we see a general broadening of the arsenic band, and we see that the higher energy states are pushed upwards and the lower energy states are pushed downwards. The same can also be observed for the unoccupied barium band. This reduces the size of the gap and lowers the overall spin flip energy. We also found that with increasing manganese doping, this overall distortion becomes more pronounced and eventually the gap will close, which is something that should be verifiable in experiment. In addition, the hybridization of manganese with these itinerant states gives rise to the magnetic coupling, which mediates the effective manganese-manganese interaction in this material. Now we move on to the meat of our results, the exchange constants. The exchange constants, which are defined in the Heisenberg model, describe both the nature and strength of the magnetic coupling. A positive exchange constant means that we have antiferromagnetic coupling, whereas a negative exchange constant means that the coupling is ferromagnetic. Furthermore, the constant J here is actually the product of a coupling constant and the local manganese moment squared, which is how we obtain units of energy. In this plot, the exchange constants are shown as a function of distance for intraplanar neighbors and interplanar neighbors for 3 different hole doping levels, which are all indicated in the legend. We note that the intraplanar results and interplanar results both lie on the same rough universal curve. Now for no hole doping, we see that the interaction is antiferromagnetic and tapers off quickly with distance. When we do include hole doping, which is what we see for the red and blue symbols, we see that for further neighbors, a ferromagnetic interaction is activated, while for nearest neighbors, the coupling remains antiferromagnetic. This indicates a competition between a short-range superexchange interaction, which is providing that antiferromagnetic coupling, and also a longer-range ferromagnetic interaction, which can be identified in the end as an effective double exchange interaction. I'll explain what I mean by that in a couple of slides, but first, we actually now have enough information to discuss the puzzling reduction of the manganese moment in experiment. The robust antiferromagnetic exchange interaction for nearest neighbors indicates that manganese singlets must be forming in this material, which will cancel out and not contribute to the net magnetization, which of course was suggested by the authors of the original experimental study. So, as a naive first model of what is going on, we can check if a random distribution of manganese moments that are allowed to decorate a square lattice, and where we set nearest neighbors to antiferromagnetic alignment and all isolated atoms to a ferromagnetic alignment, can explain what is going on. Now, since we are in the dilute limit, we're going to ignore clusters of 3 or more manganese atoms. It should be noted that including them will just give a small correction. When we work out the combinatorics, we obtain the following expression, where we see that the magnetization depends on the hole doping level, which in principle we can obtain from our density functional theory calculations, and then the expression also depends on Y, which is the manganese doping level. We fit to the magnetic moments in our calculations to obtain m of x, and then we compare our results with experiment, which we see in the plot. We do see that we get a reduction, so this is at least somewhat promising, but overall the agreement is not good. In particular, there are 2 problems. One, the reduction is just too small, and worse, the trend that we see is in the wrong direction. Notably, our results are decreasing with increasing hole doping, whereas experiment moves in the opposite direction. Something else must be at play here. We return again to our total energy calculations. We take a look at the energy difference between a faraway ferromagnetic pair and an antiferromagnetic nearest neighbor pair. When we look at the following plot, we see that for most hole doping levels, there is an energetic preference for the formation of singlets. This indicates that there might be a statistical weight that prefers singlet formation. Furthermore, in the experiment, the thermal preparation protocol was to anneal the sample to 1000 Kelvin, then slow cool it down to room temperature. This provides plenty of thermal energy to promote singlet formation, so we should check the singlet formation in a sort of thermodynamic equilibrium. So we need to return to our combinatorics problem again. We again start with that square lattice, we set the number of manganese atoms that are total in our system, and then we portion off a certain subset of those atoms to be in singlets. We work out the total combinatorics, take the natural log, and then we obtain the entropy in the dilute limit. Note that in this expression, n is the number of lattice sites, m is the total number of manganese atoms, and k is the number of manganese singlets. This expression can then be plugged into the free energy formula, which will then minimize with respect to the number of singlets. And at the end of it all, we'll obtain the following reduction coefficient that describes how the manganese moment behaves with respect to different dopings. Note that we have the following definition for beta, where delta E is obtained from the following plot, and T, of course, is the temperature. Also note that throughout this calculation, we again assumed the dilute limit, which required the use of things such as the Stirling formula. So how does this new model compare with experiment? Well, the last ingredient that we need is the temperature for our model. we recall again that the actual protocol for the experiment was to anneal to 1000 Kelvin and then slow cool it down to room temperature. So our value of temperature should lie somewhere in between these two values. However, we can't actually assume that at any point in the experiment that the singlet formation truly reached thermodynamic equilibrium. So our temperature is going to be effective. Here, we're going to choose the value of 500 Kelvin. However, we should note that this is in the end a tunable parameter. With this chosen, how do things compare? Quite well, especially considering that this temperature T is the only tunable parameter in our model. Two things to note here. First, the overall reduction is of the same magnitude as experiment. And even more importantly, the trend with hole doping now moves in the correct direction. Therefore, the moment reduction observed is due to singlet formation in some sort of thermodynamic equilibrium. So what we see here is that the magnetization of a sample depends on the thermal protocol, and so we predict, for example, that quenching the system, as opposed to slow cooling it, could lead to enhancements in the magnetization as high as 3 Bohr magnetons. Having successfully explained the reduction of the magnetic moment, we can now turn our attention to explaining the exchange mechanisms that are at play in these systems. We argue that the magnetic interactions in these systems are a combination of superexchange and some form of double exchange, and I've been arguing this for a few slides now. First, we should review what those are. So here we're going to review superexchange in the context of density functional theory. The basic picture is that you have two neighboring manganese ions, and that there is an effective amplitude for a d electron to hop from one manganese to another, which we parameterize by the value T. Note that here, effective hopping refers to the electron going over an intermediary atom, such as arsenic in our particular system. There is a Hubbard splitting between spin up and spin down, and it is given by the value U, which in DFT is equal to 5 times I, where I is the Hund's rule coupling. Now, if two of your nearest neighbor manganese ions are ferromagnetically aligned, this will lead to a splitting of the occupied levels like so. When you occupy it with 2 electrons, as you see here, there is no net energy gain. On the other hand, for an antiferromagnetic alignment, hopping needs to proceed from an occupied state up to an unoccupied state. This will lead to an overall downshift of the occupied states by the value T squared over U. When you occupy it with your 2 electrons, you get a factor of 2 in front. So, by letting the system become antiferromagnetic, we get an energy gain of 2T squared over U. Therefore, the superexchange interaction typically prefers an antiferromagnetic alignment. This is also a short-range thing, as longer-range neighbors will require additional hoppings, and so the corrections quickly become quite small. Here we review the classical double exchange, which was originally described in papers by Zahner and also de Gennes. In this picture, we have a collection of manganese sites that have 5 3d electrons each. The Hund's coupling on each site is very strong, so there is a sizable Hubbard splitting between spin majority and minority levels. A hole exists in this particular system, and it will propagate through the manganese orbitals. We should remind ourselves here that the itinerant carrier and also the local moments belong to the same species of atom, manganese. Now, like with the superexchange discussion, there are 2 magnetic arrangements that we should consider. For a ferromagnetic alignment, a hole can hop from one site to another rather easily and achieve delocalization. This will give rise to a 1-electron band that has width of the order Z times T, where Z is the coordination number of the manganese site. For an antiferromagnetic alignment, for holes to propagate, one of our electrons needs to be promoted to an unoccupied state, which, as we recall, is Hubbard split by energy U. This will lead to a 1-electron band with bandwidth of the order Z times T squared over U. So what we see here is that in our double exchange description, there is an energy gain on the order of T when the magnetic configuration is ferromagnetic. We can also see that this gives rise to a long-range interaction. The classical model of double exchange that we described on the previous slide we should recall only applies when the itinerant carriers and the local moments belong to the same species of atom. To summarize, the basic picture again was this. We have a local moment which polarizes the itinerant C directly surrounding it. This will then interact with the rest of the C, adjusting its charge density, and then eventually it'll go on to interact with another separate local moment. This self-consistent feedback loop can be explicitly quantified in the following Feynman diagram. In this case, the vertices are the interactions with two separate local moments, which are parameterized by the Hund's coupling. And of course, mediating this interaction is our itinerant C. Now, this classical view of the double exchange cannot be strictly applied to our system, as the moments and holes are of different types. Remember, the moments are manganese, but the holes are of arsenic character. Therefore, we're going to need to modify our view a little bit. So again, we'll begin with a manganese atom that is Hubbard split into spin majority and minority bands by a value U. Crossing these bands is an unpolarized arsenic-like band. So what we'll do is we'll allow that arsenic band to hybridize with the manganese, which, as we recall, will broaden the overall band. More importantly, this will lead to a polarization of the arsenic-like holes at the Fermi level. Now, this interaction we just described, where the holes and moments are of a different species, is also called the Schrieffer-Wolff interaction, and it was originally put forth in the context of Kondo theory. Again, the polarization at the Fermi level can be described by the same Feynman diagram, with the key difference being that the vertices are now effective couplings described by the Schrieffer-Wolff theory, and given in the formula below. We should also note that the polarization of the arsenic states is in a direction opposite to what you see for manganese. This means that the vertices will each pick up a negative sign. In the end, though, this will not matter, because we're going to multiply each of the vertices together, everything will be squared, and so any minus signs will drop out. So, in the end, since we have the same diagram, everything is squared and minus signs will disappear, we see that we actually have the same effective interaction as the classical double exchange picture. So the ferromagnetic interaction in our system can be viewed as an effective double exchange, in which the coupling at the vertices is a modified expression that depends on the location of our occupied manganese 3D band and the Hubbard U splitting between spin up and spin down. So, in principle, the magnetic interaction is tunable. This, of course, holds promise that the Curie temperature could be driven higher by substituting arsenic with something like antimony or phosphorus, because this might place the occupied manganese 3D band elsewhere. Of course, further work in this direction is needed. Finally, I would like to briefly comment on how the interaction changes as the size of the Fermi surface changes. So up till now, we've been dealing with small dopings, which of course gives us small Fermi surfaces. In the context of this polarization diagram, we saw that this gave rise to double exchange. So what would happen if we increased the size of our Fermi surface? Well, the actual polarization diagram will not change. So what we'll do is we'll write down a simple toy model for this diagram, calculate the susceptibility, and see how it alters as the Fermi surface area is increased. And we end up with the following picture. As you can see, as the Fermi surface area goes up, our susceptibility acquires an oscillatory part. And we know what this is. This is just the RKKY interaction. So double exchange, RKKY, it's just the same interaction in different limits. Or, put another way, they're two different sides of the same coin. This might seem like a bit of a pedagogical tangent, but it is an important point to drive home, as the dilute magnetic semiconductor literature has used different terminology to describe the physics of this polarization diagram. When we're in the small Fermi surface limit, in the literature it's usually been identified as the Zener or PD model, and has been discussed as being fundamentally different from double exchange. The main point of contention is whether double exchange, by definition, requires the existence of either an impurity band at the Fermi level or non-equivalent charge sites on manganese. Our broader view is that it's all the same thing. the details are contained within the vertices, and since the whole thing is squared in the end, you formally get the same effective interaction. In summary, I talked about a new and exciting dilute magnetic semiconductor, barium zinc arsenic doped with manganese. This material is versatile, and we saw that it has transparent physics. We saw that if we hole dope the material by replacing the bariums with potassium, that nearest neighbor manganese pairs will have an antiferromagnetic coupling, but non-nearest manganese pairs will have a ferromagnetic coupling. The magnetic interaction in the system we saw is a competition between superexchange and double exchange. The double exchange is due to the Schrieffer-Wolff mechanism, which gives rise to an effective Hund's coupling. And this effective Hund's coupling is exciting because it means that our double exchange interaction depends on the position of the manganese 3D band. And that means that the Curie temperature in principle may be tunable. I would like to thank you for your attention, and if you would like to learn more about this study, I encourage you to check out the following rapid communication, which I have written at the bottom of this slide.